Good afternoon, everyone. We'll have a short speech about our trip to Abu Dhabi and how it is participating in an international robotics challenge. My name is Christopher, and this is Christian. We are both studying electrical engineering. What is it? Yeah, we are both studying a Master of Science in Electrical Engineering here at DTU, and we were. Okay, cool. Yeah, in March we were participating in an international robotics challenge in Abu Dhabi, where we brought this robot for DTU. The Mohammed Bin Zayed International Robotics Challenge is obviously an international robotics competition held in Abu Dhabi every second year. There are $2 million in prize money and $3 million in sponsorships. The reason why it's called Mohammed Bin Zayed International Robotics Challenge is because it's initiated by the Crown Prince of Abu Dhabi, and thus it has his name.
The competition. The competition consists of 3 separate challenges and a grand challenge. Challenge one is with a flying drone, which has to find a moving target in the arena. This is the target you can see here, and the drone has to land on the target while it's driving around in a figure 8. The second challenge, which is the one we were in, consists of a UDV, which is the robot we brought here. The UDV needs to navigate in a partially defined environment. In our case, it was a large field, and it had to find this box here and operate Evolve on the box. Obviously, this all had to be autonomous, so there could be no human intervention in the procedure.
Yeah. The third challenge was a treasure hunt for drones, where you had to pick up different objects on the ground. Some of them were moving around, other was static, and the drones had to fly around an arena and pick up different objects and drop them into a dropping zone. Yeah. The two of us, we were part of the second challenge. These you were participating in all the challenges. However, we were working on the robot you see here. We started the preparation 1.5 years in advance before the competition, November 2015, where DTU applied to participate in the competition. And in January this year, they got the final acceptance to go to the finals, or we got the final acceptance to go to up. Like our prototype of our first robot, before we bought the thing you see here, or like assembled the robot. Yeah.
Yes, so the trip to Abu Dhabi was in total of 10 days. Me and Christopher, we made the vanguard, so we landed earlier than the rest of the group, and we set up sort of our camp down there. Because when we left Denmark, the robot wasn't entirely functional yet, so we still had some work to do. The robotics field, or the competition field in Abu Dhabi, was located on the Formula 1 track in Yas Island. They had set up large arenas with nets for the drones, so they could not escape if something went wrong. Overall, it was a very impressive setup they've made, and we certainly felt like we were in professional hands. We had 2 rehearsal days where we could practice our robotic procedure before the grand event or the competition. Obviously, those they went very well for us, and we were quite confident when we went along to the competition. The competition itself was very intense, with a fierce competition between the teams, and we had a very intense competition with the University of Bonn, who was the university that went along to win the competition. Yes. Yeah. As we mentioned, this is our robot, which we built here at DTU, or we assembled here at DTU. Overall, it consists of the terrain hopper frame, which is the mobile robot frame in itself. And on that, we have mounted the UR5 robot arm, which is made by a company over in Odense. Yeah, as this robot are not able to see, or we don't have any cameras on it, we have mounted a force sensor on the robot arm to sort of feel the environment.
Okay. First, when we started out, so it's very important for a robot to kind of perceive its environment, to know where it is and how to operate. And what most people have done for this competition was to use computer vision. And we also started out using computer vision by mounting a camera, as you see here, on the end effector of the robot. And then using the camera to look at the panel and analyze the different tools and the valve. So this is the valve it has to turn, and there are 6 different tools. It had to pick the proper one and then turn it 360 degrees. However, this was really sensitive to noise, and it was kind of hard to make it robust. So we came up with this other idea to, instead of using a camera, we wanted to feel the panel and try to use the robot arm to touch everything and kind of feel its way like a blind man would do. Yeah, so that's what we have here. On your approach using force feedback. So basically here at the robot arm, there is a 6 degrees of freedom force torque sensor that can feel force and torque along the 3 axes. So it gives feedback to the robot, so it knows when it's touching something, and it can feel how hard it's pushing towards the panel. So what we did was we kind of feel the tools in order to find the proper one, pick the proper one, and then we started turning. Yeah, but more about that later.
So the challenge 2, which was the one we were participated in, was separated into sort of several subtasks which we had to solve in order to be successful. Initially, the robot would be located in the starting box and should find the box, which was and should find this the black box on the field. To do that, we have mounted 2 laser scanners on the robot here in the front. The laser scanner is a rangefinder, which means that it can sense the distance using a laser sensor, which effectively creates a 2D, sort of a 2D vision of the world. Then we can estimate where the box is in this laser scan and navigate towards it. As I mentioned, the laser scanner only sees the world as flat. So in order to find the box, we need to, the box essentially becomes a line in the environment. So we need to find the line in the field and then drive towards it. And when we have the box in the field of view, then we have to estimate which is the correct side of the robot, which we do by having the multiple laser scanners, because the box is not unique in the height. So we can estimate the correct side of the box using the laser scanners. As our robot here is a Ackermann-steered robot, we have to navigate like you would do in a normal car, which means that whenever we're driving, we can only we cannot move sideways. So we have to sort of parallel park in front of the box. So when we were approaching the final position of the box, we would sort of parallel park like you do in a normal car. And then whenever the laser scanners could see that you were within the target position, we would initiate the gripping procedure, which Christopher will tell more about.
Yeah, so whenever you're solving a problem, it's a good idea to narrow it down to kind of a more simple problem in a way. So what we did was like we defined a new workspace for the robot consisting just of the panel. And in order to define this workspace, we had to kind of find the origin of the coordinate system for the robot to operate in. The way we did this was to first find the corner here, and we basically did this by making the robot kind of touch the panel on the sides and in the middle. And in the same way, we could use the kind of touching function to estimate the position and the angles of the board. Yeah. So the way the problem was put up, everything on the board was kind of predefined, like the positions. So we knew approximately where to go. So after we had found the corner, we could go to the tools and try to measure them. So as soon as the work frame had been defined, we had to find the proper tool to use. The valve was a fixed size, but however, the spanners could be put in different orders. So the way we solved this was to make the robot feel each spanner. So it went to the first spanner and kind of measured the length by dragging down, and as soon as it felt resistance in its force torque sensor, it knew it kind of had reached the head of the spanner. And then it did this for all of them. And as soon as it had measured all the spanners, it could sort them with respect to length, and then pick the proper one to use for turning the valve. Yeah. So as soon as the proper tool had been picked, it had to turn the valve. And it was really important to be sure that the robot actually engaged with the valve. So the way we did this was approaching the valve at a 45 degrees angle. And as soon as it felt it hit the valve, we would like slowly turn it until it engaged with the valve. And after that, it will start turning faster, and then in the end reach the 360 degrees. We have a video of it here.
Yeah. So now we'll just show a video of the sort of our best run at the competition, so you can see the entire procedure all together. Yes. As I mentioned, down here we have the starting position where we had to start the entire competition, and then the robot had to navigate all the way to the box itself and align with the front of the box, and then pick the correct tool and turn the valve. Yes, so initially we would just drive towards it, and then as soon as we saw the box, we would start navigating relative to the box. I think they'll show it now. And then when the robot detects that we are on the wrong side of the box, it would start to drive around the box in order to be able to align with the front of the box. And as you see here, you can see the parallel parking procedure I mentioned earlier, which the robot needs to do to be properly aligned with the board.
Yeah, so it tries to align at a 90 degrees angle towards the board, and that's why it kind of moves forth and back until it reaches a proper positioning. And that's what happens here. So it starts the robot arm, and here we see the robot. First, it tries to feel if the robot is positioned correct with respect to the panel. So it tries to measure the angle of the board, so it can kind of adjust the angle if it's not 100% correct. And now it's filmed. Yeah, those are the spanners. So now it tries to find the corner of the box in order to find the relative position. Yeah. And for robustness, it's just, since we approximately know where the valve is, we try to measure it one more time to make sure it is where we actually think it is, and then correct in case it's a bit off. And the same for the tools. Yeah. And now it'll try to measure the length of the tools as previously explained. So it kind of grasps it so it knows where it is, and then it moves downwards until it reaches the head of the spanner. And then it keeps on going for the rest of them. Initially, we thought it might be enough to just measure the width of the spanners, because actually the gripper we are using from Robotic is able to measure width as well. However, the difference between the spanners are in millimeters when you compare it to width, whereas if it's the length, it's centimeters. So it gave us like a bigger fault margin towards picking the right one. And you might ask why it's measuring all of them. Can it see when it finds the right one? And technically it can. However, there is a bit of deviation in the measurements. So we had like a small interval. We said if it's within this, you should pick it. Otherwise, you should measure all of them to be sure you pick the right one. And this is why it's basically measuring all of them to make sure it is actually the right size it picks. And that's what it does here. So it goes down, pick the correct spanner, and takes it out. And now it has to engage with the valve, as it does here. So it's at a 45 degrees angle to make sure it's within the spanner. And then it drives slowly to kind of engage. In this approach, it uses the force feedback in the sensor to make sure it's to make sure it has the right contact with the valve. Because if it pushes too hard or too soft, it might not engage probably with the valve. So yeah, that's what you see here. Yeah, as soon as it engages, it goes fast. Yeah, and here it completes. Okay. In the competition, we were actually only 2 teams finishing the task with full points. And even though we didn't win, we were the only team not calling a reset at any time during the competition. So that's also a thing.
Yes. So as we mentioned, we didn't quite manage to get the first place, but we did get the second place in Challenge 2. The winning team were the University of Bonn, which they won on time. We were the only 2 universities which actually completed the challenge, so I think we are quite happy with our performance. As mentioned, we did our run, the one you just saw, in just under 4 minutes, and the winner did it in 1:30. But yeah. Fortunately, there were also a medal and a trophy for the second place, which we brought here. We didn't get part of the $350,000 unfortunately, but we didn't go home empty-handed.
Yeah, a bit of perspective. Yeah, it was really exciting to be a part of this entire competition. And it's going to be in 2 years again. So some of you might be at DTU in 2 years. And we can really recommend participating in those competitions. Yeah, everyone was showing really good experience. And it was a really good atmosphere when you walked around and talked to the other teams. And you kind of had the opportunity to network with other teams, meet other universities who are really passionate about what they're doing and their labs and research. So yeah, it gave us a lot. And after all, we were quite happy and satisfied with our second place. Yeah. So yeah, if you have any questions, feel free to ask. If not, that was it. Any questions?